Power quality issues cost industries billions every year, and most of them never get properly diagnosed. If you work in the field, you know the frustration. This podcast is for you. Welcome to Power Quality Decoded, brought to you by Power Monitors Incorporated. Find us at powermonitors.com. Let's dig in.
Hello, everyone, and welcome to today's white paper webinar. Today, we're talking about electrical vehicle charging, the technical aspects of how these chargers work, the different types, and also the effects on power quality for the utility on the explosion of this new type of load. So this white paper really has two parts. The first part are the details of how the different charging systems work. There are a variety of residential and commercial charging protocols and plugs and systems. And then we'll talk about power quality impacts. So I'm going to introduce Caleb here, who is the author of the paper, to talk to us through some of the different charger technologies.
Thanks, Chris. What I'd like to go over a little bit is just basics and some of the terminology and the implementation of how the charging infrastructure has been set up here in the U.S. We had a paper about EV charging probably 7 or 8 years ago that we put out. And this is meant to be an update to that as the technology has advanced dramatically in that period. 6 or 7 years ago, the state of charging was basically DCFCs or DC fast chargers were limited to CHAdeMO. It's a Japanese standard that you still find on Japanese vehicles today. And they're the only automaker in the U.S. that still ships with CHAdeMO charging port. Everybody else has moved to CCS, which is combined charging system, or to Tesla's NACS. There are 3 basic levels of charging. There's level 1, level 2, and level 3. Level 1 and level 2 are what you're going to find in commercial residential installations. They're either 120 or 240 volts. Level 1, for instance, is 12 to 16 amps, 120 volts. And then level 2, the 208 to 240 volt circuits can go up to, I believe, 80 amps. Those really are not big power quality headlines. The DC fast chargers that are really kind of changing. And so I kind of wanted to go over the fact that, CHAdeMO is being phased out in favor of these new systems because CHAdeMO was limited to 50 kilowatts, whereas the new CCS and NACS charging systems peak out at about 350 kilowatts, so about a third of a megawatt, which obviously is a drastic difference. One of the fascinating things is that Tesla, being the largest manufacturer and the biggest uptick in EV manufacturing in the U.S., has kind of driven innovation across the field. So their NACS charging systems have become the go-to standard for everybody. So all new vehicles manufactured in the U.S. are going to come with the NACS plugs. And the slowest charge you're going to find for Tesla at this point is 250 kilowatts. So there is going to be probably fairly dramatic uptick in those. Anecdotally, we're here in rural Virginia in the Shenandoah Valley. Not a lot of public fast charging here. Like I said, the CHAdeMO is being phased out. And so naturally, that's the vehicle that I chose to drive around for the EV testing. So you go to some of the local chargers and those peak out at about 150 kilowatts, whereas the Tesla chargers that are around here are at 250 and 350 kilowatts. That would be one of the bigger things to look for and how it's going to affect the grid in a more general sense. For the level 1 and level 2, there's a little bit that utilities can easily do. And it's, basically the rate structure to mitigate some of that. If you want to push load shaping off, like for instance, a good load shaping strategy could be dropping the cost of residential consumption to, say, 10 to 18 cents per hour overnight. And that would allow customers with EVs to perform their charging overnight versus peak loading during the middle of the day. But again, those really don't have a large impact on power quality other than if you've got a lot of residential users that start installing level 2 chargers at home, you may have to look at some transformer sizing issues as those continue to increase in those areas. Apart from that, that really basically covers the fundamentals of the charging infrastructure and where things sit here. And Chris is going to go into some of the power quality impacts with those.
And as Caleb mentioned, on the residential level, power quality impacts are mostly on just kind of base load. And it would take an entire neighborhood with some higher level 2 chargers to make an impact. And it's really because without any staggering of those charges, those cars are all charging roughly at the same time. Everyone gets home from work, they start cooking dinner, and they start charging the cars. But with intelligent phased chargers, spread out charging with rate structures that encourage that can help level the load so that that doesn't put too much peak load on the grid. It's when we get into these fast chargers that we get into the more interesting power quality issues. So where these are very high loads and have a fair amount of harmonics. So these are nonlinear loads and they're very large loads. And they also change relatively quickly as cars pull in, start charging, and then drive off. Because Caleb mentioned these are 350 kilowatt, even in some cases higher per car, and that adds up fast if you've got a lot of chargers. From a utility standpoint, the most immediate impact is, of course, the load. On a feeder where suddenly a megawatt high-speed supercharger site is placed, and that feeder wasn't sized for that sort of load or multiples of those on that circuit up front. So you may end up with reconductoring or heavier load on the transformer at the substation than expected. But also with the harmonic content, these chargers in many cases aren't terrible, but they're not perfect. They usually have a better power factor than harmonic distortion. But it depends on the quality of the charger. Here we have some examples in the white paper of the current THD, voltage THD. And I'm going to pull up peak canvas so we can just see this directly. This is the Tesla supercharger. And if we just start with the interval for voltage and current, we have many days of charging. And if you zoom in, you can see the load pattern. When cars pull in, they start charging. And that's usually a step increase in current. Here there were no, at this point, there were no cars plugged in, and then one car plugged in. And it starts at the highest power and then gradually tapers off. So from that standpoint, it's a friendly load because it doesn't cycle that high power off and on rapidly as the charge tapers. It gradually reduces the current. And here you can see they stack. As more and more cars pull in, we're seeing the total transformer loads. So you have multiple cars kind of with the current stacked on top of each other. And so you'll see a step increase as a car pulls in and plugs in, and then the current gradually decreases as that car becomes more and more charged, and then another car also plugs in. So that's a step increase in current, and then you have two cars that are now tapering off, and then one car disconnects, and then they step down to zero. And so you see this pattern over and over of a step increase and then a gradual ramp down. So that's the characteristic load pattern of a supercharger or other high-power charging system. You see these kind of sawtooth or triangle wave patterns where the current abruptly increases, and that can be a step change in the voltage, but then the current ramp down is more gradual. Now you can see that the voltage wasn't affected that much. There are times when the voltage does change at roughly the same time, maybe not exactly the same time. Some of these are regulator adjustments, but other times the voltage is not affected. In this site, this is a fairly large transformer that is somewhat resistant to the changes in voltage. Now let's take a closer look at the harmonic content. We will look at the voltage and current THD. So the green is the voltage distortion. The blue is the current distortion. And we can see that the voltage distortion is still pretty good. It's in the scaling here, it's a little bit off. It's around 2% over the whole time. So the current distortion is not pulling the voltage distortion. If we take a look at flicker source. So now we're looking at voltage minimums, current maximums, and instantaneous flicker level here in the bottom to see if a flicker is being caused by this, by the load. And if it is, how bad is it? So here's the instantaneous flicker. It's fairly low during the whole recording, except for a few excursions where we're going over 2 for IFL. And what we see for voltage is we have voltage sags that aren't really correlated with the current. The current is not causing these voltage sags. So in this location, the rapid changes in current are not causing rapid changes in voltage. This is a fairly strong system and a large transformer. If you have a weak system, the effects could be more significant. So that is something to look out for because you have these abrupt increases in current. That's the potential for a rapid voltage change, which could lead to flicker. Now let's take a look at some of the waveforms. And many of these waveforms are typical. You can see the current abruptly switch off or abruptly switch on. Here, the red is voltage, blue is current. And we have many waveform captures when the current switches off, and then we'll see many when it switches on. And you can see the distortion here. Let's look at the harmonic distortion when at the beginning. We see on the voltage, we see a fairly prominent 5th and 7th harmonic. We also see on the current 5th and 7th harmonic. We also see some 3rd harmonic current, which is not typical for 3-phase harmonic loads, but with a bit of voltage imbalance, you will see that. We can actually take a look at the voltage imbalance on this waveform. Here we are, it's fairly low. We're just a few tenths of a percent, but that's enough to cause a bit of 3rd harmonic on this load, which is, again, most 3-phase nonlinear loads don't have much 3rd harmonic, but this is enough to produce that. But we see the dominant harmonic for voltage is 5th and 7th, and that is what is most likely to be caused by these EV chargers. And in general, any three-phase nonlinear load is usually fifth and seventh harmonic, and then you'll sometimes see other multiples of 6 plus or minus 1 as you get higher. But here, fifth and seventh is by far the dominant. So on a feeder level, those are the two harmonics you want to look out for. And you'd also want to look out for resonances, which are very common at 300 hertz, which is the fifth harmonic. And then these are mostly RMS events. As the current switches off or on, we can look at the RMS view and see the voltage or the current transition. And here, again, the voltage is relatively stable. We're shifting less than a volt on a 40-volt system. So this is a fairly large transformer relative to the amount of current we're seeing. But, of course, it depends on how many cars are stacked. There are times in this recording when we have many cars together. So you're going to see small fluctuations when only one car is there, and then it tapers off. But occasionally you'll see, for example, here, the maximum current is when we happen to have a lot of cars. This is the highest current in the entire recording. Here we're seeing much higher current than the others. This is multiple cars at a very fast charge. Yeah, no waveform triggered, so that did not affect the voltage much. You can see there's no minimum voltage change. So this is a stiff system here. What we can also see is the sensitivity of these loads to perhaps voltage sags. If we zoom in on a portion where we have some utility sags, these sags, for example, this sag here in green is not caused by the load because there's no current flow whatsoever. So these are sags that are happening on the feeder from other customers. And a couple of times these sags happen during the charge. And what we see is that the charger is unaffected by that. So here, this flat portion of the current is at maximum charge, and we have some deep voltage sags during this time, and that really caused no effect on the current. So these chargers are fairly resistant to these sort of deep voltage sags, unlike, say, a motor or motor protection. And you can actually see, if you look closely, a little increase in current. They increase their current as the voltage drops to keep a constant power. We can look at the waveform for one of these sags to confirm that indeed the current didn't really change at all. And you can see that at high currents, it's a nearly perfect waveform. The power factor is very good. You see some crossover distortion, 0 in the current. But overall, it's a fairly low distortion current waveform. And the current distortion actually gets worse as the current lowers. So as the battery starts to taper, the distortion on the current will become worse and worse, but the current itself is dropping. So in an absolute sense, it doesn't matter as much. There'll be some intermediate point, usually around 60 or 70% of full output, where it's the worst on the voltage. Now, if we look at the RMS capture here, we can see that it's a deep voltage sag. We're dropping about 25 volts on a 40-volt system for about 3 cycles. But that didn't really affect the chargers at all. These charging systems are usually pretty insensitive to voltage sags. They're most sensitive to absolute voltage and voltage imbalance rather than voltage sags. And then the problems they will cause are most likely harmonic distortion. They can cause rapid voltage changes if the system is weak compared to the size of the charger, especially if you have many chargers on feeder. But harmonic distortion is generally the most common problem for these. And if you are troubleshooting an electric vehicle system, you want to, of course, put a monitor at the transformer secondary. If the transformer feeds other customers, you would put it at the service entrance of the EV charger system, and you want to leave it for at least a full day, but ideally an entire week, to see the full pattern of vehicles pulling up, charging, and leaving. For example, in this recording, there was only one day where we saw the worst case current load. So you don't want to just leave it for an hour or two or even a day. You want to leave it for a fairly large amount of time to capture the combination of all the bays being full and at maximum charge, because that doesn't happen every day in many locations. And you want to make sure you enable harmonic recording, or at least THD for voltage and current. Periodic waveform capture is useful in a flicker because you want to not miss any of these power quality issues. Good question. What would be the solution for harmonics and sags? So that's a big question. The solution for harmonic distortion usually is based on who's in violation of what standard. If the charging system is exceeding their allowable current injection per IEEE 519, generally that would involve harmonic filtering on the customer side, the tuned filters that block certain harmonics or active filtering systems. If the voltage is in excess of the 519 standard, then the utility would need to mitigate that, often by detuning capacitors or finding other customers on the system that are in that violation of 519, or decreasing that system impedance, upsizing the transformer, upsizing conductors. But that really depends a lot on the relationship between the voltage and the current and which side is causing more distortion. And then for sags, that's a completely different sort of problem. That again depends on if the sags are caused by other customers that are drawing excessive inrush currents, then those customers need to mitigate that with soft starters or VFDs, or if the sags are caused by faults on the system, vegetative faults or other types of intermittent shorts like that, then on the utility side, they would perhaps increase tree trimming, go to cover conductors, other sorts of mitigation for preventing those faults, or better sectionalization, isolating different customers with reclosers. Well, that's all the questions we have now. Again, if you have a question later, feel free to give us a call or send us an email. And thanks for attending.